Hello folks, today in this video we're going to talk about more magnetism. This time we're going to take a look at some other specific magnetic effects as well as talk about the magnetic fields produced by different things than just charges. Let's go ahead and get started. So our first thing to talk about today is the torque on a loop of wire. This is a very specific situation, so you'll always be able to recognize when this is happening with magnetism. It's going to be the only torque that we talk about. The idea behind this is if you have a loop of wire that you've placed in a magnetic field, it actually won't experience a net force. This is because the force on those different wires, remember that a magnetic field does produce a force on a wire, will cancel out because if the current is going up this way, it'll produce a different force than when it goes down the other way. But it will produce what is called a torque. You might remember that torque is the rotational analog of force. So instead of making this loop move back or forth, it will make it rotate, or it will make it to spin. This seems like a really weird example, but this is actually super critical. This is the basis for producing electrical motors. So the way that you make turn electricity into mechanical energy is you turn a current through a loop of wire in a magnet, and then you can actually make that loop spin, and then you can use that spinning to produce all sorts of different devices that depend on a motor, which is pretty cool. So our equation for the torque on a particular wire, torque, remember, has the symbol tau, is NIAB sine of theta. So very similar equation to things we've seen already. Torque, of course, is this little tau, and it's measured in Newton meters. This capital N is the number of loops in your wire. The idea being is that the more times you loop around the wire within your magnet, the more of a magnetic torque that you'll get on that wire. So you can increase that torque by just looping the wire around more in that magnetic field. It then depends on I, the current, which we've seen before, and then A here. This A is not amps. This A is the cross-sectional area of that wire. So how big this wire is in terms of area. So you take the length and the width of that one if it was a square and use that for your area. If it was a circle, you'd use pi r squared. And then finally B is the magnetic field, which we've seen before measured in Teslas. And of course this one has an angle. This angle here, sine of the theta, is the angle between the field and the normal or perpendicular vector for the area of the loop. What that means is that if your field is pointing directly through the center of that cross-sectional area so that it's pointing that way, that's a 0-degree angle. And that actually means that the torque would be 0. So there is no torque at a 0-degree angle because, again, the sine of 0 is 0. And then there's max torque when that is 90 degrees. That means that the actual loop is lined up with that magnetic field there. So let's take a look at an example of a problem that you could do with one of these. It says here, rectangular 20-turn coil of wire of dimensions 10 centimeters by 5 centimeters carries a current of 0.1 amps and is hinged on one side. It is mounted in the XY plane and at an angle of 30 degrees to the direction of a uniform magnetic field of magnitude 0.5 Teslas. Wants to know what the torque is acting on the coil about the hinge line. So we know our equation. We know that torque, tau, is equal to NIAB sine of theta. So I just got to plug in my numbers here. N is the number of turns or loops in the wire, and so you'll see the word turn a lot, so that's 20. The current going through my wire is 0.10 amps. Then I need my area of my wire. Because this is a rectangular loop, it would be length times width. I'm going to change those to meters though, so 0.1 meters times 0.05 meters. And then lastly, B is my magnetic field, which was 0.5 Teslas. Then lastly, I have to include the sine of my angle, which is sine of 30 degrees. Put that in your calculator. When I did that, looks like I got about 0.0025 Newton meters as my torque. B then here is what is the max torque on the coil? Well, to get the max torque, remember that that occurs at an angle of 90 degrees. So you'd plug that in now rather than the 30 degrees and run the same calculation. I'm not going to write the whole thing out, but it's all the same idea. And when I did that, you can check, I got 0.005 Newton meters. So just a bit larger than that 0.0025. Okay, so that's the torque on a wire. Another interesting situation that seems weird, but I'll get in a second about why this is important, is that particles in a uniform magnetic field will undergo circular motion. So you might remember talking about circular motion back in Physics 1, and that's actually very important for charged particles. So if you put a charged particle, you might remember that we use the right-hand rule to figure out what direction it's going to be moving in a magnetic field. So this diagram is a little complicated, but let's start off just with a simpler scenario. Magnetic field's still inward, and you have a positively charged particle moving to the right. If you use your right-hand rule here, it's moving to the right, and then the field is into the page, and so the force on that one would be upward, which is the exact opposite we have in this scenario, because this one is negative. So if you don't mind, I'm actually going to change that. Let's make this a negative charge. So then we just flip it, and the force on that would be downward. Well, the idea behind this diagram here is if the force is downward, but it's moving to the right, that's going to cause the particle to move in a circular fashion. Here, then, if you have your negative charge there, it's now moving downward. So if you did the right-hand rule, the field, or sorry, the velocity's downward, it's still into the page for my B, and now my force is to the right for a positive one. I got to flip it, and so it's to the left for a negative particle. And so you can see that that force is always going to be pointing toward the center, hence why you get circular motion. So you can set the force, magnetic force, remember that FB equals QVB sine theta. We're going to ignore the sine theta here. We're just going to always assume it's at a 90-degree angle. That's my force. And you might remember that the force of circular motion is mv squared over r. So I can set those equal to each other and then solve for r. We're going to be interested primarily in the radius of the circle that it makes when you put an electrical charge and move it in a constant magnetic field. So solving that, you get mv divided by qb. Now you might be thinking, okay, but why is that important? Well, it's actually very important when making devices called cyclotrons or synchrotrons. So you might have heard of these before, particularly in the medical field. These are actually very important. They are a source of various kinds of radiation. For example, if you wanted to produce X-ray radiation, you might use a cyclotron in the medical field. Or if you wanted to produce certain types of medically interesting isotopes for use in radiomedicine, where you use radioactive isotopes in the body, we use cyclotrons and synchrotrons actually to produce these. We also use these to probe very interesting physics. Back like 10 years ago, it was really big in the news that we had built a very, very large synchrotron in Europe, the Large Hadron Collider, if you might have heard of that before. The Large Hadron Collider is in like the border between France and Switzerland here. This is a picture of it. And it's famous, one, because when they say Large Hadron Collider, they're not kidding. The diameter of the loop is 5.3 miles long. And this is a picture of the tube that they have where they're shooting charged particles, protons, electrons, and other nuclei through a magnetic field and having it spin around. They use this to probe high energy physics and learn new things. We've actually discovered brand new particles using these before as well. I was lucky enough, I was at Cornell for a while, and I got to work the closest big synchrotron we have around here is at Cornell. It's at CHESS, the Cornell High Energy Synchrotron Source. And it's actually located underground underneath some of the soccer and football fields at Cornell, funny enough. This is a very blurry picture of physicists actually riding their bikes through the tunnels where those synchrotrons are going. This is one of my favorite physicists there who is running through there. His name's Hans Bethe. So those are what synchrotrons are. They're very useful, and they use kind of this principle here. So I got a fun little problem for us, which is how large would you have to have a synchrotron be in order to accelerate an electron to a speed of 5% the speed of light in a constant magnetic field of 0.5 teslas. So I put some useful constants on your reference table because you will recognize and know, of course, that you would need to have the mass and the charge and such of your electron in order to solve this one out. So you need that M, that V, that Q, and that E there to actually solve this. So my pen isn't working, so I can't quite draw it out, but I'll talk you through this one here. So we're going to be using that equation. Going back here. That R equals mv over qb, where m is the mass of your electron here. If you look on your formula sheet, the mass of an electron is 9.11 times 10 to the minus 31st kilograms. So very, very, very small. Then we want to do the v. It says here my v is going to be the speed of light, but only 5% of it. The speed of light on your formula sheet is 3 times 10 to the 8th meters per second. So if you take 5% of that, when I did that on my calculator, I got 1.5 times 10 to the 7th meters per second. Then in my equation, I'm going to divide by Q. Q is the charge of the electron, so 1.6 times 10 to the minus 19th coulombs. And then finally, B is going to be your magnetic field, which is 0.5 Teslas here. Put that in your calculator, solve it out, and I got 1.7 times 10 to the minus 4th meters. So not very much, actually. It's pretty small. So you really don't need a very large synchrotron to be able to get to even high speeds, like 5% the speed of light. But as you get closer and closer, this gets much, much, much larger. And that's why we have to build such bigger ones. The one in the Large Hadron Collider can do 99.9999 something percent the speed of light. It's very, very, very fast. Okay, we have a few last interesting things to talk about. We're now going to talk finally about how do I calculate that B? So far, the magnetic field strength has just been given to us. We've been like, oh, okay, cool. B is the magnetic field strength. But how would I know how strong the magnetic field is? Well, we can calculate it for a few different scenarios. This first one here is the magnetic field produced by a straight wire. Current through a wire always produces a magnetic field, and for a wire, it is circular. It actually goes around the magnetic field. So you can kind of see that up here in this illustration, this diagram. That field goes in a circle. And as you get further away, of course, you would imagine the magnetic field would be weaker. If you go to the smaller circles, it is going to be stronger. First off, if we want to know the direction of the magnetic field, it is given by the right-hand rule again. But now I can't do like the, this one with the 90-degree angles because this is a circular field. So instead we use a different version of the right-hand rule, which I use my thumb and then I curl my fingers around like this here. The idea being, I'll get that there, that this, my thumb, is telling me the direction of the current. Again, still the V, but now what I imagine is that if it's going upward, then I curl my fingers around and I can see that the magnetic field points that way. So if you're looking at this picture here, and it's difficult, of course, to kind of see there, but if I go upward and I curl my fingers around, I can see that it's going, this way around my wire. So in a counterclockwise direction. So that's always going to give you the direction of your magnetic field. If you wanted to see, there's a good picture of it there, of somebody using the right-hand rule to figure out the direction of their field. All right, pen's being a little frustrating there, so we'll see if I can get it back and working. Next is the equation to calculate this. If you want to calculate the magnetic field, it would be mu naught times I divided by 2 pi r. What's mu naught? Mu naught is another constant for us. It is called the vacuum permeability of space. It just has a number to it. It's 1.26 times 10 to the minus 6th. And the unit of this is henries per meter. Just know that's it. Henries per meter. We won't talk about henries much because we're not going to get into inductance and things. So just use that and then you should be good to go. Next, I, we already know, is current. And then R is the new one here. That's the distance from the wire. So how far away from the center of that wire you want to calculate the magnetic field. Okay, the next scenario is What if I put two wires next to each other? Well, each of the wires is going to make a magnetic field as depicted in this picture here. So each of the wires will be in the magnetic field of the other one, and that will produce a force on each wire. So there will be a force between those wires there, and we call it F parallel. So F of two wires that are parallel to each other exert a force. Now, we actually don't calculate the actual force. We typically think about the force per unit distance. What that means is that you're taking into account how long the wires are there. So to calculate that, the force per unit distance, F parallel over L, that's going to be that mu naught, same number that we just saw, I1 and I2, which are the currents of each of the two wires, and then R, which is the distance between the two wires that you actually have. So very, very similar equation there. And then you can memorize that the force is attractive if the currents are in the same direction, and repulsive is if they are in opposite directions. So the forces attract if they're in the same, and repulsive if they're opposite. The next scenario is, what if instead of having a line of wire, I now want to think about a loop of wire? Well, that will also produce a magnetic field. And instead of being, like that circular pattern, what actually happens is that the magnetic fields all line up. So it produces more of like a straight magnetic field through that current of wire, so loop of wire. So this is that picture kind of depicting that magnetic field as it goes up through that wire. How do I figure out the direction? Right hand rule again. What you're going to do is curl your fingers. Actually, the way I do it is curl my fingers around in the direction of the loop. So if I'm looking up at that picture over there, I can see that the current is flowing around the wire. So this is always the circular portion. And then that means that the magnetic field is going to point up through that loop. So that gives you a way to figure out how that works. You could also think about it like, hey, my thumb is showing me which direction. And then if I curl my fingers, they're going to be curling upward there as well. Then there's another equation to calculate it. To get the magnetic field inside a loop of wire, it's going to be mu naught times I, the current, divided by 2R, where big R here is not the distance from the wire, it's the radius of the loop that you're working through. And we're going to be thinking mostly about circular loops, so R makes sense in that context. So here's a little question for us to look at here. It says, what is the direction of the magnetic field in each of the following scenarios? So go ahead, take a second, give them a try, and pause the video if you want, and then come back and we'll talk about the answer to these ones. So the first one, wire with a current I flowing upwards. So remember, it's always right hand rule. So I've got my current flowing up. If I want to think about what direction that's going to go, I would say it's going to curl around that way. So the answer for this one, let's see if my pen is working now. Yeah, no luck still with the pen. I'm sorry, guys. So the direction for that one then would be kind of like back around the wire and out back in front. I would call that direction counterclockwise because it's going around the wire in that direction. So counterclockwise for us there. Then it's got wire with current flowing clockwise. So my current is flowing this way there. That way I get the right one for the mirrored perspective. That wire is flowing that way, so I use my right hand rule. Loop around, I'll use this one, that correct direction, so I can see that it's flowing around there, and I would get it to be going into the page there. So that current is going to be flowing through the center of that loop into that page. Then I've got the bottom one here, wire with a current. Wire with current flowing counterclockwise there. So again, using the right hand rule, my current now flows this way, and it looks like, yep, I get it coming out of the page toward me. So that current would be flowing, yep, out of the page. And then lastly, I've got the side view of the top loop. So this one here, the current is going, it looks like a back around and then out toward me. So kind of flowing like this, right? So if I use my right hand and loop with that current, I get it to be going down through the top of that loop here. So hopefully those examples were helpful for you to kind of take a look at direction for these ones here. The last thing, as I've always said, I want to connect us back to something that's like real and important, and why we would care about the magnetic field through a loop is for making a device called a solenoid. A solenoid is a useful device by making a bunch of loops in a coil of wire and running a current through them. Solenoids are found everywhere. They are often used to turn, like for an electrical device, to be able to move something. So, like an electronic lock would use a solenoid to actually physically move the lock back and forth using a force. But they come up in tons of different scenarios. Solenoids are very cool. If you wanted to calculate the magnetic field in a solenoid, you're going to take that mu naught that we've known from before, the number of turns or like loops in your solenoid, I, of course, being the current, and then divide by L, which is the length of your solenoid. Okay, folks, thank you so much for watching this video. I'll let you get out of here. Have a fantastic rest of your day.